Welcome to the AMATIC 2015 webinar series. My name is John Oakes and I am the Professional Development Coordinator for AMATIC. And today's presentation is Teaching and Learning Strategies for Infinite Series, Limits of Partial Sums with Bob Cappetta. And this presentation is sponsored by the Mathematics Intensive College Mathematics Committee of AMATIC. And AMATIC is the American Mathematical Association of two-year colleges, and our core value is building expertise and exhibiting leadership in the teaching and learning of mathematics, enhancing personal growth, and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. And for more information, please visit our website, amatic.org. And please note that the views expressed by the presenter are not necessarily the views of AMATIC, and any commercial products mentioned by presenters are not endorsed by AMATIC. And WebAssign is proud to support the AMATIC webinar series. So now I'm going to switch to the presenter slides. So while I'm waiting for those to come up, hopefully I get the ones with the right year on it here, Bob. I'm going to actually introduce Bob, and if you want to welcome him in the chat room as I do that, that would be great. So Bob has taught at Illinois Community Colleges for over 25 years. He is a past president of the Illinois Mathematics Association of Community Colleges, and he is an active member in the Math Intensive Committee of AMATIC. Bob earned a PhD in mathematics education from Northern Illinois University, and his research interests focus on teaching and learning concepts from calculus. So with that being said, I'm going to turn it over to Bob, and we're looking forward to your presentation today.
Great, thanks, John. And I want to thank all of the participants for spending some time on a Friday afternoon. I am here outside Chicago. If you haven't already told me where you are logging in from, I would appreciate having some idea where folks are. And I look forward to spending the next hour with you. And I would like you to participate, so I will ask several questions, and I will take a look at the responses in the chat box when we get there. So any quick answers? Why do you think Calculus 2 is difficult for large numbers of students? I'm just curious what some of the responses we're going to get here. David says proofs. No doubt about it. We spent a lot of time doing proofs in Calc 2, maybe not so much in Calc 1. John and Diane are saying series. Well, we're here talking about series, so I think many of us probably agree with that. Following sets of rules, and I agree with Susan completely. Poor algebra, poor trig skills, Calc 1 skills, etc. And notice trig and algebra is showing up again. And the reality is I think we wind up teaching some trig and algebra when we're in calculus. And no concrete answer again. Each proof that we look at, or each series that we show whether it converges, in essence is a proof. Now here's some of the things we get from the research. We move from procedural mathematics to conceptual mathematics. So in a sense, series is when that happens. And as Cullinane says, in general, when we get beyond the early calculus, we have to be able to adapt new perspectives. The nature of the activities changes. And as we've seen in the chat boxes, it is different with proofs. The concepts of series are difficult. No concrete answer indeed. So let me ask you this question. So all of us teach second semester calculus. What do you really want students to know? What are the key ideas you want students to get from teaching a course on series or teaching a unit on series? As we wait for the responses. And we'll see what comes up. We welcome 5430226. Good to have you on board. Okay. Elmira says they need to understand what series are. And that's an interesting point because I've done a little research on that and students don't know what a series is. They confuse the notion of series and sequences. Susan says they want to know about convergence. But what does convergence mean? That is also something that requires looking at many different concepts at one time. Johanna says, what are transcendental functions? And a wonderful example, e to the x, sine x, cos x, are all defined by series. Evaluating derivatives and integrals of not so nice functions. I'm with you there too, Diane. I just don't know if that always shows up in the curriculum. I think that's something we use as mathematicians, but I'm not sure that's something students always do. Understand how series behave differently. I agree with Elmira there. And we'll see what other sorts of ideas we have. Foundations of advanced calculus. What I tend to say is that series are the DNA of many important functions. As we saw, finding derivatives and integrals of not so nice functions, if you want to do that analysis, one of your best strategies is going to be looking at it from the perspective of series. Why is it important for students to study series? I think we saw many answers there. Now let me ask you this question. After students complete a section on series, what do they know? So once the course is over, at the end of Calc 2, what do students really know about series? They know that they're glad that it's over. They know they don't like them. Okay, I cannot disagree. The reason I ask that question is I fear that students memorize routines to get through the test, and these concepts are never internalized. So they may actually do well on an exam and then forget everything a day or two later. And I think the reason this happens is because they're not focusing on what these things mean conceptually. So that's what I think we need to change. We need to think about what do we want students to know after they finish the course. And one of the things that I think is most important, which is shown up in the chat, is what is a series? And what does it mean for a series to converge? These are not simple questions, and I'm not sure we spend a whole lot of time on it. Now, John makes an interesting point in that we don't really go back and spend a whole lot of time on series after we finish Calc 2. I don't know if they show up at all in Calc 3. I certainly spend some time on series and differential equations, but I think his point is a good one. Maybe we need to make an effort to reintroduce these concepts. And as mathematics majors, we certainly have seen series as important concepts in later courses. I certainly appreciate all of the fine things. Certainly, Laplace transforms. Don't cover it all in DPQ. Okay, do Laplace instead. Let's see. All right, let's take a look at some of the recent research that was done. And I want to thank Paul McCombs from Rock Valley College for inspiring me to look at this topic 5 or 6 years ago, and he has also shared a lot of the research with me. As you can see on Kung and Spear, very little is known how students think about series. Now, the second one I think we would agree with. They confuse sequences and series. Third one, notation's a problem. And wouldn't you agree that when you draw that capital sigma, many students get frustrated quite easily. And you'll notice they talk about cognitive overload. They're just unable to manage the difficulties they have there. And this last one is important in that if you think you can identify a student's understanding by looking at their written work, you're just wrong. The research shows that when you talk to students, they might be able to do the problem correctly on paper. But when you ask these sort of probing questions, you soon recognize that they have very little understanding of the concepts. So if you want to see where students are, what they do, you really do need to do some one-on-one sort of interviewing to help you understand what they currently perceive from these topics. Okay, let me ask you this question. If we're looking at textbooks, and I would assume most of us use the same 5 or 10 textbooks that are out there, what do you think are the primary teaching and learning objectives for series? Based on the textbooks, what are the goals that the textbooks have for students to learn? I'm curious if we have some agreement on what those topics are. Okay, Taylor series. Sometimes I wonder, I'm with Elmira, it's not clear what their goal is, how to apply an appropriate test for convergence, as we see with 2 in a row. Choose the appropriate test and prove whether or not the series converges. I think that's right. I think that's really what they want. David's point about Taylor's series, I would agree with too. Maybe that's the ultimate goal because that helps us understand these transcendental functions. This is what Gonzalez-Martin says about textbooks. Ahistorical, decontextualized fashion, where algebraic routines are the goal. So it's one more chance for us to practice algebraic routines. As we see applying convergence tests, maybe you could argue are there. Very, very few graphical representations. And are there any applications? You know, we spend all this time talking about series, but how many applications do we see for series? Does anybody use any? Are there any applications that you've seen? Using a computer to approximate it, if that's what David means, certainly we've seen that. But the ahistorical fact, I think, is a challenge because the development of series and series convergence was very difficult historically. Yet students see it in class looking at it as a completed notion. This is the idea, this is how we do it. But the development was tricky, and we'll talk a little bit about that today. So here's some of the other research that we've seen. Students believe that 0.99 repeating is less than 1. That's a challenging notion. And in fact, even some AP calculus teachers have said that 0.99 repeating is less than 1. It's a very subtle concept. And I guess this notion, I think it's less than 1, is really reminiscent of Zeno's paradox. Yet those same people that think 0.99 is less than 1 tell me that that geometric series converges and equals 1. They know that. So why is that? What are we missing where they think that the repeating decimal is less than 1, yet the series converges? And here are some of the answers that students have given us. So they say it doesn't end, so it can't be compared to an integer. And they also say infinitely close to 1 is not truly 1. What does that mean? And then small differences, mathematicians don't care, so it's just rounding. And it really comes down to, what does it mean to converge? And I don't think you answer that question properly unless you discuss what convergence means, unless you discuss what a limit is, as we see in David's comment, and unless you discuss what the partial sums are. You know, so these are the sorts of issues that we need to look at to try to make sense of this, to try to move our students forward in their understanding. Welcome Meg to our group here. So here's some research that's been done recently. Martin used interviews to ask experts what they thought about Taylor's series. And what was most troubling about Martin's research is 4 of the 16 experts, mathematicians at universities, use what I call the nth term convergence test. That if A sub n converges, then so does the series. You know, many students say that. But if you're going to have experts, you know, maybe not concentrating carefully, are going to make that error, it's not hard to believe that students will continue to make that error. So talking about historical series. So this is one of the first times that this came up. I think it's in the 17th century. So 1 minus 1 plus 1 minus 1 plus 1 minus 1. What does that equal? Rondi said it equals a half. Now we know with our modern definition of convergence, that's not correct. We would say the partial sums diverge so that the series diverges. But you know, I think it's a pretty good wrong answer. I mean, on average, it's a half, in essence. And if you extend your interval of convergence for that series, you can see how he was able to get that. So to me, it's kind of an interesting, incorrect answer. For many years was the standard approach to this problem. But we had to change the way we count. And the way we changed the way we count is by looking at partial sums. Now, this is a standard infinite series sort of problem that's done in pre-calculus. We say 0.333 repeating is x. We can multiply both sides by 10. And then we subtract. 10x minus 1x is 9. 3.33 repeating minus 0.33 repeating is 3. X is a third. Let me ask you this question. Is this a valuable strategy to show in Calc 2? You have a few responses. Elmira says no. David said time constraints prevent it. I'm curious what else we get. David Rose says yes. I do show it. Diane says they fail to see it as an infinite series. I agree. I agree there. Susan tells me it's an algebraic manipulation. And yeah, I think Dina and I are on the same page. It is an opening. They've seen it before. You can connect what they're doing now to what they've done in the past. But I also agree with my friends who are saying no, because, so how can I say both yes and no? I think it's good to connect what they're doing now to algebra, but it's also good to show them where this sort of thing fails. So one of the goals that I have in teaching series is by showing counterexamples, like this one. All right. So if you say x is 1 plus 2 plus 4 plus 8 plus 16, similar in many ways to the last example. Doubling everything, we get this. Subtracting, everything cancels out, and you get x equals -1, which of course is ridiculous. And we know why it's ridiculous. We know it's ridiculous because the partial sums do not converge. But do students know this is ridiculous? And my problem is I don't think students know what the partial sum definition really is. John says, didn't say in the instruction they had to use a series, and so the instructor used the algebraic method and was marked wrong. Yeah, well, I guess I could understand why people might do that. So some older research, David Tall and his partners, 1978. Students get the notions of sequence and series muddled, and the research I've seen has absolutely shown that. They don't know the difference between a sequence and series. And if you think about it, if you're looking at series, there really are two sequences. The sequence of elements as well as the sequence of partial sums. So that's a tricky issue. More recent research, even good calculus students, A students in Calculus 1, struggle with convergence. And I most certainly have seen this. Maybe some of that is writing proofs, understanding what these ideas mean. 2000 research, a rich schema, a internal perspective of what these things mean, how all the pieces fit together. They need to look at series as a limit of a sequence of partial sums. And as Diane is saying, they don't get that. And I completely agree. Now, the formal definition of a series as a sequence of partial sums does not replace in students' minds the notion of an infinite sum. Add them all together. The students may write on paper that they think it's a sequence of partial sums, but when you ask them more in-depth questions, probing questions, you will soon realize they don't really believe what they say, which is why you've got to be careful looking at written work. But here's our fundamental issue. Again, before. We have the terms of this in the sequence of partial sums. The students must coordinate these two ideas to make sense of the concept. All right, so if we're talking about sequences of partial sums, in my mind, the telescoping series is where you start. And we can see on this first term, second term, third term, fourth term, but the positive 1/3, negative 1/3 cancel, the negative 1/4, positive 1/4 cancel. So many teachers that I've seen, frankly, just cross those out and say that it's 1 plus 3/2. Is that wise? Is it wise to just cross out the terms that cancel and then say that the answer is going to be 1 plus 1/2? But this is a standard technique. Now, to be fair, the textbooks don't typically do this, but when people teach, that's pretty standard. It's pretty standard. What you need to do is you need to give them some alternate types of problems. So here's a telescoping series where you'll notice that things cancel. Negative 3/4, positive 3/4 cancels in a sense. Negative 4/5, positive 4/5 cancels in a sense. Does this equal 1/2 plus 2/3? We know the answer to that. We know that it doesn't. But you need to look at the partial sums to be able to see that. So here's a teaching suggestion. You have to look at counterexamples. Students develop concept images. This is going back to Binner's work, which don't necessarily have to agree with the concept definition. They can state a definition. Yet when you ask them what something means and you ask them to create their own words, they're very different. So you need to challenge students' concept images by giving counterexamples like the one I just showed you. That canceling the terms is not going to be sufficient to determine whether or not the series converges. So here's our Grandi series, right? The first partial sum is 1, second is 0, third is 1, fourth is 0. So I hope it's obvious based on our present definition of convergence of series that series must diverge. There's no way that series can converge given our current definitions. So here's how I suggest the repeated decimal problem should be taught. So, in the chat we saw someone said students do not see the repeated decimal as an infinite geometric series. So if you write out the fractions, I hope that's a little clearer. Now, from this, can we see what S sub n is? So the first term, 3/10, second term, 33/100, third term, 333 thousandths. Is that clear to us what S sub n is going to be? And this is what we get. Will students be able to do that? Will students be able to express S sub n in that way? I hope so. Now, we know how we do geometric series. You typically show that a geometric series will converge if the absolute value of the common ratio is less than 1. And then the sum of the geometric series is the first term over 1 minus the common ratio. We know how to do that. And I know that students can apply that correctly in this case. But can they come up with the partial sum? I'm not sure most people do. But I would argue that it's valuable to encourage students to think about the geometric series that way. Returning back to the divergent geometric series, 1 plus 2 plus 4 plus 8 plus 16, we see the first sum is 1, second is 1 plus 2, third is 1 plus 2 plus 4, fourth is 1 plus 2 plus 4 plus 8. Maybe it's a little clearer to us what S sub n would be. So again, you ask the question, can students see that? Can students generate a rule for S sub n? We can see that doesn't exist. But here's the real question. Have I completed this problem? Have I done everything that I have to do or that I'm supposed to do? And I would argue there's a little bit of a problem with this in that I am saying S sub n is 2 to the n minus 1. I am arguing by looking at those partial sums, but I didn't prove that with induction, right? And I'm not sure using induction is necessary. But I think it's important for us to at least acknowledge as educators that we're asking the students to look at this and generate a formula for S sub n that we're going to assume is correct or hope that it's correct without going the extra level. Let's see. So David writes, I can't get over the notations for the initial sequence are A sub n and the partial sum notations are S sub n with A sub n as terms of the series. Now, that's a good point, David. I think I agree with you there. So should we change that to S sub k maybe? That's a thought. I appreciate the suggestion. Okay, here's the telescoping series approach, and I think this is the way all of us teach it or should teach it in terms of having the students find the partial sum. So there's our first term is 1 minus a third, our first sum. Second, 1 minus a third plus a half minus a quarter. Nothing is canceling, nothing is subtracting out yet. S sub 3, 1 plus a half minus a fourth minus a fifth. S sub 4, 1 plus a half minus a fifth minus a sixth. S sub 5, 1 plus a half minus a sixth minus a seventh, as we cancel those terms. So I hope at this point the students can look at this and say, what is the nth term going to be? So as we examine this, we say, well, 6 related to 5 is 5 plus 1. 7 related to 5 is 5 plus 2. N plus 1, n plus 2. And of course, these terms go to 0. 1 over n plus 1, 1 over n plus 2 goes to 0. So if we want to have the limit of this series, we take the limit as n goes to infinity of S sub n, which will indeed be 1 plus a half or 3 halves. So I argue this is the way that telescoping series should be taught, and frankly, most textbooks do it that way. But it's easy to get in the habit of just crossing out terms and saying the answer is what's left. That gets you in trouble. about this telescoping? What's interesting about this, if we look at these series separately, right, the sum of n over n plus 1, that will most certainly diverge. The sum of n plus 2 over n plus 3, that will certainly diverge. So that's kind of interesting. But we will indeed get a sum from this if we look at the partial sums. This series will converge as we get the cancellation we need, but the error terms don't shrink to 0. The error terms are going to go elsewhere. So here is my first sum of the first term, 1/2 minus 3/4. Second one, 1/2 minus 3/4 plus 2/3 minus 4/5. And maybe you can see what's happening here. You'll notice the 3/4 subtract out. So I get 1/2 plus 2/3 plus 4/5 minus 5/6. And there we go for S sub 4 and S sub 5. Students are not going to like doing this. And I have to be honest, I just gave this question on a test that I gave yesterday. And looking at the results, I'm not terribly pleased. The bright students were able to get S sub n. The weaker students were having quite a bit of trouble with that. This is what we see. When you're looking for the rule that is going to define those sums, this is what we're going to have. 1/2 plus 2/3 minus n plus 1 over n plus 2 minus n plus 2. In Calc 1, we show that those limits are both -1, -1. You could certainly prove it with L'Hopital if you want to use more sophisticated mathematical machinery. But either way, we wind up with what? As those limits go to infinity, 1/2 plus 2/3 minus 1. One thing I like students to do is to use a spreadsheet, to use a graphing calculator, use something to sum up the first 100 terms, first 1,000 terms, whatever is reasonable. And if they do that, they get a feel for where the thing is going. I would hope that would give them enough evidence to say, maybe it's not just 1/2 plus 2/3. So using computational schemes to kind of lead you into the direction you want to go. All right. Here's a problem I wish I could take credit for, but was used in Martinez-Planell in a recent publication. 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7 plus ... I'll give you a chance to look at that for a minute and think about how would you handle that? What strategy would you use? Partial fractions is one suggestion. Telescoping series, use partial fractions. All right. Well, let's see what happens with this. Interestingly, 1 over 1 times 3 is 1 over 1 minus 2 over 3. You'll notice 3 minus 2, 1 over 3. 1 over 15 is 2/3 minus 3/5. 1 over 5 times 7 is 3/5 minus 4/7. Well, why not move the parentheses? Can I reorganize so it's 1 minus 2/3 plus 2/3, minus 3/5 plus 3/5, minus 4/7 plus 4/7? Elmira says I can't do that. Well, let me ask this question to the mathematicians in the audience. When would that be fair? What type of a situation would we have to have that would enable us to regroup? Absolute convergence. There we go. Exactly right. Is this something that students are going to understand? I don't think so. But hopefully they're not going to do this. So this sort of thing, again, is going to work if we're absolutely convergent. But that is not going to give me the answer. The answer here is not 1. And if you did the first 100 terms, the first 1,000 terms, I hope that would indicate that we're not going to get an answer of 1 here. So is S1? No, we know it's not. So looking at this, then, we need to build our various partial sums. So I've got the work up there: 1 minus 2/3, 1 minus 3/5, 1 minus 4/7. And we hope that the students can start to see the pattern. To prove it again, officially, you would have to do what? You'd have to use the principle of mathematical induction, but I'm not sure that's worth the aggravation at this point. But doing enough of those partial sums, I hope that students can see that the nth partial sum is 1 minus n plus 1 over 2n plus 1, which we can then see how that has to behave. But I think it's important to give the students these examples to challenge their faulty concept images. They look at these things and they think it's going to behave a certain way just by canceling terms, and you recognize, I don't think so. Okay, so let's talk about teaching strategies. We've looked at a few problems here, and those problems are designed to create cognitive dissonance, to use a term that we talk about in cognitive psychology. You want to cause the students to rethink their untested ideas. You want to challenge them. And these sorts of counterexamples, I think, work very well. Now, I don't think the textbooks do a really good job using technology or demonstrating technology. With a spreadsheet today, you could get the first 1,000 terms summed in no time. And I have students write graphing calculator programs, and even there you could get the first 500, first 1,000 terms most of the time to get some idea how these behave. But the textbooks rely on these algebraic strategies almost exclusively. And frankly, I think a lot of people teach these courses using algebraic strategies almost exclusively. And yes, that's the proof. I get that. You want to prove that something converges. You're going to need to use algebraic strategies to prove it. You cannot prove it with a graph. You cannot prove it with technology. I get that. I get that. But the technology, the spreadsheets, the graphs give you an indication of whether or not something is going to converge. It gives you some evidence, not a proof, but some evidence. And then once they look at the evidence, we can have students make hypotheses based on that analysis. And sometimes those things are going to be wrong. John is saying he's doing it on an Excel spreadsheet, and the students still want algebra. Yeah, I mean, the students are part of our culture. They want an algebraic trick. I get that. So this is something that I found in Gonzalez-Martin, which I really like. So this is showing that the harmonic series diverges. And it's a nice visual representation of that, in that 1 is certainly more than a half is more than a half. If I take 2 fractions more than a quarter, that's more than a half. Right? If I take 4 fractions more than an eighth, that's more than a half. 8 fractions more than a 16th, that's more than a half. This is the method of Oresme. This is the first proof that was done that the harmonic series diverges. So whichever student came up with this, I applaud that person for a really nice visual approach to show that that series is going to have to diverge. What do we typically use? We typically use an integral, right, and show that it's bigger than a divergent integral. But I like this. I like this proof of Oresme. Now, Wolfram alpha. We love it, we hate it. Well, Wolfram alpha is a wonderful tool for getting various partial sums. So if you want the sum from 1 to 100 of 1 over n, fine. We can get that. It's about 5.187. And the students are also fascinated on Wolfram alpha by these ridiculous fractions. Fractions with so many digits in the numerator and denominator. So you ask a student, well, the first 100 terms of 1 over n are giving us 5.187. What do you think? Is this going to converge or diverge? You know what students are going to say. Students are going to say, oh, I think that thing is going to converge, because after 100 terms, it's only 5. Of course it's going to converge. Well, we know that's not the case. Here's 1 to 10,000 of 1 over n, which is 9.7876. 1 to 100 was in the 5 range. 1 to 10,000 is in the 9 range. So where do you go from here? Yes, Dina, I'm using Wolfram alpha for good, not for evil. I'm with you. 1 to 10 million? 10 million terms, and I'm only at 16.69. I've been teaching this stuff for 27 years. I'm still fascinated how slowly this converges. Apparently, David agrees with me. So here's the question we have to ask. No technology allowed. I don't want you to go on Wolfram Alpha. I don't want you to use a calculator. Can you predict how many terms would be necessary so that the partial sum of the harmonic series would be more than 100? Is anyone brave enough to make a prediction? I think our numeric friend, 5430226, billions and billions, to quote Carl Sagan. Okay, well, that's a interesting answer. Anybody else brave? I hear you. All right, well, let's talk about it. The answer is approximately 10 to the 44. So I guess officially that's billions and billions. But just to give you an idea, the age of the universe is about 4.3 times 10 to the 17 seconds. Billions to the billions power. Okay. So if you want to get more than 100, you need more seconds than the age of the universe by a large factor. Billions times as many as that number. So, I mean, indeed, the harmonic series diverges, but very, very, very slowly. And I think the students find this kind of fascinating. And notice we're still looking at partial sums. We looked at the partial sum for 10 million or whatever it was to get a feel for how that's working. Here's a visual. So sometimes graphs could be misleading. I think if students look at this graph, they may say, you know, I think this just might converge, and they would be wrong. So it's not enough to have a graph. You need to have some mathematics behind you. You need to have some analytical approach, an algebraic approach to prove that. Well, if you like 1 over n, this is even more fun, right? So we're looking at the partial sums for sum as n goes from 2 to infinity of 1 over n log n cubed. And you can see after, what is that, 10 million, we're still only at 2. And we can create all the functions we want that are going to diverge slowly, but that does diverge. But you make the case to the students, or does it diverge? Excuse me. I don't know. Looks like that converges. That's going to 2.06396. So we'd have to prove that using strategies. All right. Now here's one of the problems with this technique. If you start your series section by defining series, by defining sequences, and by defining convergence as convergence of the partial sums, you are very limited in the number of problems that you can solve. What we've looked at today are geometric series and telescoping series to get a feel how these behave. But if you ask the students to find the nth partial sum of the sum as n goes from 1 to infinity of 1 over n squared, what are the chances they're going to get that right? Well, the reality is it took Euler, one of the greatest mathematicians in history, to solve this problem. It was one of the great unanswered questions. So we're dealing with the situation that, yes, partial sums are important. Talking about partial sums to prove that things converge, I argue, is crucial to help students understand this. But you're not going to be able to do it for the sum of 1 over n squared. Now, proving that this converges is very easy using the integral test or a similar kind of a thing with pictures. That's easy to do to prove it converges, but to prove what it converges to based on the nth partial sum is going to be a challenge. So when we're going through this discussion of convergence of partial sums, we've got to say, the reality is, for most problems, we don't know. We don't know what S of n is. That's when we need the algebraic approaches to prove that things are going to converge. So what is the nth partial sum of the sum of 1 over n squared? The answer is this from Wolfram Alpha. Again, I hope that's Wolfram Alpha for good, not evil. So we have this psi function of n plus 1. I would assume this must go to 0 as n goes to infinity, pi squared over 6. I have to say I could not prove that. Maybe some of you could. But the limits of partial sums cannot answer everything, only a small class of functions. So, formalism. So let's talk about the Weierstrass School of Teaching Mathematics. If we are really teaching convergence of sequences, epsilon n proofs would be what we'd have to use. It is my thought that relatively few people teaching convergence of sequences use epsilon n proofs. Now, to do one or two, I'm with you, but to do them on every time, I think that's unwieldy. I'm not sure that that's possible. But you could get criticized for not doing it, I'm sure. Now, the mathematical induction, we're looking at these partial sums and we're saying, based on our evidence, it appears that the nth partial sum is so-and-so. We're not proving that with mathematical induction. So is that the appropriate amount of formalism? And, you know, I've talked to analysts who really hate the idea of using graphs and tables because they say they can misinform students. And you're sending a bad message by having students look at graphs and tables when they don't tell the whole story. And again, I get that in mathematics, that that's part of it, but I want people to be able to connect their work to other representations. And the graphs and the tables, in my mind, enable us to do that. So yeah, I'm just curious. Any concepts on these things? Susan says, or comments, Susan says in building a foundation, it's nice to have a visual. I'm with you. Okay, monotonicity test, sure, showing that monotonic sequences converge. I think that's an excellent point, David. Thank you for that. Other notions? It's probably fair to say that no two people are going to agree on what's the right amount of formalism. And I think that's okay. You know, everybody in his or her class has to decide what they can live with, what they think is best for their students. Because I don't think there's one right answer to this question. Okay, let's talk a little bit about teaching strategies. No, Susan talks about the fact that the class goes so fast we don't have time to understand. I'm with you. How can we build in these sorts of things in the classroom? Again, our goal is for students to remember these things. Our goal is to have them use it in the future. I think that's a real serious issue. So here's some of the teaching strategies that Cullinane shares. Take a look at what we're doing. Is what we're doing the best thing that we can do? Looking at these informal notions, again, that's what we get. I think that the tables help us with these informal notions. The graphs help us with these informal notions, help us develop the idea. Abstract via concrete. Well, I think there's more than one way to do things, but if you start with concrete representations of things, it's easier for students to make that leap into the abstract. And, you know, most importantly, can you link what students are doing now with what they've learned before? That's why I like that 0.33 repeating issue. They've seen that in pre-calculus. Let's look at that with the mindset of calculus and see how does that change? How is our perspective different looking at the limits of partial sums? So I think these are all excellent suggestions. All right, well, that's all I have. So I'm more than happy to open the floor to questions. So if there's things you'd like to ask me, if you'd maybe throw those in the chat, and I'll do my best to answer them. And looking at some recent things, David says, introduce the strict definition and a proof or two, but leave it to advanced calculus for epsilon n. Okay. George talks about improper integrals. Of course, improper integrals would be taught usually just before this, right? Because we need to have the improper integrals before we move on to the series, since we use the integral test as one of our first ideas. All right. Questions? As we wait for questions. Yes. You'll notice that it says slides are available here at google.com/site/rwc/file. So those are available there. One that is called Webinar, and you'll be able to download those. In fact, my old series talks are up there as well. So if you're interested in this one, you may be interested in looking at some of my previous talks. Teaching Calculus 2 online, boy, that is tricky. I have not tried to do that. I do teach statistics online, I teach math for nurses online, and I record all my lectures. And I have students submit something every week so I can make sure they're on top of things. That's probably my best answer for teaching Calculus 2 online. If you record your lectures, then you can use technology. You can show them Wolfram Alpha. You can show them graphing calculator sorts of things. You can show them some good graphs. So I would probably do that. My problem with teaching online is the students don't collaborate very well. So if you have a suggestion for how to get students to collaborate in an online Calc 2 class, I'd love to hear it. George is saying a sequence can be represented as a step function. I have to say, George, I haven't thought of it that way, but that's right. If you'd want to make it, I guess it's not quite continuous, but you could define it on the real number domain instead of on the integer number domain. That's a good suggestion. Dina says collaboration on Google Plus for online classes. Yes, there are good tools out there, better than there ever have been before. I just want students to use them. So I guess you have to design exercises, design experiments to get students to work together. We've got some other sorts of things. Yes. Oh, improper integral with the step function series. I had never thought of that, George. Thank you. I will consider that going forward. While we are waiting for a few more questions to come in, I hope that I will get a chance to meet some of you fine folks at AMATIC in New Orleans. I will be there for the weekend, and I will be working with Sandy and Scott on the math intensive sharing session that we'll be doing on Saturday at 10:45. So if you're interested in the direction AMATIC is taking with these calculus courses, please consider joining us for our sharing session. As well as I would assume we will have some sort of a meeting, a committee meeting. So I hope we can see some of those folks there as well. All right, let's see other things that we see here. All right. Okay, John, maybe I can turn it over to you. Any comments before we finish up?
There are still a couple of questions or thank yous. So, yes, if you haven't thanked Bob in the chat room yet, feel free to do so now. I know that I enjoyed the presentation today, and I hope that all of you did as well. So, thanks for participating in today's AMATIC webinar. If you'd like to support future AMATIC webinars, please consider becoming a member of AMATIC at bit.ly/join-AMATIC.
All right, and if I may, Sandy is reminding me that the Math Intensive Committee meeting will be on Friday afternoon. So looking forward to seeing you in New Orleans on that Friday afternoon to talk about some math. So wonderful. I appreciate your time, my friends. If you would like to continue this conversation offline, feel free to email me. I'd be more than happy to share some other ideas.
And actually, I will put Bob's email address back up on the screen after I put the survey link up as well. So let me go to the survey link right after this slide. So recordings of past AMATIC webinars, including this one, can be found at the link bit.ly/AMATIC-webinars. And so I will make sure that all of you get a link to the recording and to today's slides. So if you didn't copy all this down, you will get an email from me shortly, probably by the end of the weekend. And if you could please take 2 minutes to evaluate the webinar content.
So again, Thursday.
Yes, actually.
Session. Let's see you in New Orleans.
I did read that in the. I did read that in the program actually, because I was putting together my AMATIC schedule this past week, and I noticed there was the theme session and then the committee meeting the same day there. So yes, I hope to see all of you in New Orleans too, if you can make it. But if you do need to take the survey, or if you would like to take the survey, please feel free to actually click on the link on the screen. It is a clickable link, or you can type it into your web browser, and this is where you would request a certificate as well. So please make sure that you enter your email address in the survey so that I can send you your certificate for participating today. So I'm going to actually end the recording now.